Good morning to all. So thanks for your participation for this GIAN course for the last 4 days, and today is the last day. So hope you will enjoy our stay. Okay. So today my lecture will be design and synthesis of bulk heterojunction solar cells. Already Dr. Jagdish gave lot of inputs about bulk heterojunction solar cells. So in this concept we have a single cell. For example, in the case of your Dyson solar cell, we have two glass plates, we will sandwich one above the other. But in the case of organic solar cells, there will be one single cell. We are making a one single cell. I have working piece here actually, I will show you. So this cell, only one, where we have coating one by one, layer by layer spin coating method, and then we encapsulate and make a solar cell device. That's the one we are do. So this cell consists of glass substrate. Mostly here people use ITO, but they don't use FTO because FTO conductivity almost good, but in the case of organic solar cell, ITO is they feel better efficiency compared to FTO. So they use the ITO as one of the substrate in this case. And above ITO, they coat pedot PSS. They coat pedot PSS, one of the layer, over which they put the active layer. The active layer consists of two things. One is called electron donor polymer, other one is called electron acceptor polymer. So either they can use electron donor polymer and electron acceptor polymer. Based on the things they can change the active layer conditions actually, and over which they coat aluminum. People use gold, gold is very expensive, they can sputter aluminum over which and they can make a solar cell. So this is solar cell where we can get light into electricity. So we can apply light energy and get electricity. That's your solar cell. Whereas the opposite is called OLED, where the above layer will be difference, where we can apply electrical energy and get light energy. That's the difference one OLED. So maybe yesterday Gopalakrishnan will talk OLED, or maybe today more given by Dr. Jagdish about solar OLED applications. Okay. So design and synthesis I want to talk about here bulk heterojunction because Jagdish give more information what are the compounds they use. So we know all the literature review etc. We synthesize in our laboratory some of the organic molecule. Based on that we can fabricate solar cell. That's we want to show you in this case actually. So this slide, we know Earth receives lot of energy, solar energy. So from which we can get your global energy demand will be very small, and we get India will take only 0.08% solar energy. We can get your PV installations. We can see PV installation all over India will be very, very less. 0.08% only will be there. 0.08% will be there actually. So we can make solar cells. So in this introduction slide, we want to talk about this is the NRL, National Renewable Energy Laboratory. They give this important about the solar cells from the last 50 years and more. The first solar cell starts with multi-junction components. They can use 3-junction, 2-junction, etc. Or they use the amorphous silicon, etc. Or single crystal gallium arsenide, etc. to make a solar cell. So it starts in the year you can see 1975, okay, 1975 approximately, and starts. We can see the efficiency goes on 44%. We can notice the efficiency goes on 44% actually. Then this cost factor will be very high. People go to the pure crystalline single silicon solar cells. So this will start also in 1955 with different companies, okay, and they also goes here. You can see up to NREL, etc. And they get maximum 24% efficiency will be noticed actually. Then comes thin film materials like gallium arsenide, cadmium telluride, etc. So this will be the green one. So we can start from here 1975 this also, and this goes only 20%, maximum 20% actually. So like this solar cells are going all over the world. People start working with the last one with the EPFL, that is the organic solar cells, or emerging PV, or Dyson solar cells, or quantum dots. So they can start from 1990 onwards, and they give efficiency of maximum 12%. This is a laboratory model, 12% they can get actually, and now they are getting more devices actually nowadays actually. This is a scenario of your historical R&D laboratory form. The laboratory, how much they can get efficiency, a notice from National Renewable Energy Laboratory, USA actually. So you can notice here, this is the one where people are working in this concept. So IBM, UCLA, NIMS, Japan, etc. They are working in this to get a maximum of 12% in the laboratory scale. That's the solar cell they are doing actually. Okay. So solar cells will be very important point. What they are do? So Dyson solar cell means dyes may be visible light, 400 to 800 nanometer only they can use. But this organic solar cells, they don't want dyes of 400 to 800 nanometer. They want above 800 nanometer. So in this case, they are just matching with silicon, or we can say solar spectrum of silicon actually. It shows maximum absorbance, you can see above 800. That's why band gap is 1.2 electron volt. So if you use TaO2 in Dyson solar cell, band gap is only 3.2, it absorbs only 4 nanometer, but dyes will absorb 400, 600 or 800. So we want to move this dyes towards the other side, that is above 800, to make a low band gap solar cell or narrow band gap solar cell, which can give a more efficiency point of view. So in the first class, your demo, you have noticed P3HT. P3HT will show a peak around 400 to 600. See, there's a broad peak around 500 plus. So this is your P3HT. And in Dyson solar, organic solar cell, people use polymers like MDMO, PPV is a polymer with function group, or PCBM, very expensive material. So this PCBM, they use absorbance very low, less than 400 nanometer. P3HT, we have this one. So we have noticed these components of absorbance, they want to modify or tune this band gap towards the visible light or more towards the IR region. That's the concept of this work actually. So more focus. So we don't want your absorbance 400 to 800 nanometer. We want to focus towards 700 about to 900. So that's the concept of this organic solar cell people. They want to focus towards the low band gap, that is 1.5 to 2, 1.5 to 2 or 1.2, because silicon is 1.2, they want to make 1.5 to 2 band gap actually to get a good efficiency also can be noticed actually. So what is the difference between bulk heterojunction and bilayer? Bilayer means you are coating one by one. So you can see you put a donor first, over which you can put acceptor. So this will be two different layers actually there actually. So if two different layers are there, electron has to carry the layers to one above other. It may take some time. But in the case of bulk heterojunction, you mix the two electron and donor and electron acceptor in one beaker and then add this one completely and then coat. So this is called your bulk heterojunction. So we don't have a layer. So your donor may be either in the electron in the acceptor level, or acceptor may be in the donor level. So it may be more focusing of movement electrons can be possible in the case of bulk heterojunction. That's why it's called as the widely applied. This bulk heterojunction field is widely applied to make a solar cell concept in this scenario. Okay, so that is the concept they use this bulk heterojunction solar cell for different angles. So what they use actually, they use a planar structure. So mostly compound should be a planar. That's why. So the mostly compound they use will be planar molecule. So planar molecule polymers are planar structure. So they use polymers planar structure, and they make the electrodes are transparent. Compounds should not have any absorbance. They make a transparent electrodes in this case actually. So this is the concept of your structure of organic solar cells, where we can see glass substrate with ITO, with pedot PSS, and then we have an active layer, and then we have aluminum on the other side actually. All will be in a single glass plate, not on two different glass plates as in the case of your Dyson solar cell. So the active layer is most important here. In this case actually it may be either electron acceptor or electron donor. So mostly people use your PCBM as electron donor and etc. etc. So how to choose a molecule here? In the case of this organic solar cells, they use mostly conjugated molecules. So conjugated molecules are most important because this absorbs high light absorption. It has good epsilon value. So we can see 10 power 5 1. So you can see a polyacetylene. It has a good conjugation groups. We can use the compound as a conjugated molecules because it absorbs light absorption very high. Or it should have alternating double bond and single bond like your pyrrole, this polythiophene. Polythiophene we can see the component double bond, single bond. Okay, they got pi conjugation you can have. Or we can see delocalized pi electrons. The compound should have a delocalized pi electrons by this model. So this is good for application. So this is the importance of making choose of your conjugate molecules in the case of your organic solar cells. So if you make this compound, we can tune your valence band and conduction band. Band gap can be reduced. We can take good electron transport, solubility, and structural properties we can tune. All these properties can be very important for your application point of view actually. So if it's noted on literature, people use mostly your first compound, this is MEHPPV, the organic molecule, parent molecule, or P3HT, the thiophene base. Mostly you can see all are thiophene based. Thiophene based molecules are good conjugation, good electron donor molecule, so they are the good compound for solar cell applications. And people use PCBM, so fullerenes are very expensive molecule. So for example, if you want to make a fullerene, 1 gram of fullerene may be around 60,000 rupees approximately, so we don't want to go in this concept, so we want to make a different one. So what we want to do in our laboratory, we want to tune, we want to change the molecule, so we don't want your P3HT PCBM is a general solar cell people used, so we want to change a different one, change by Perlin moieties. So Perlin moieties we want to make in our organic lab, in our laboratory, and make a organic solar cells for different applications. So if you just choose your P3HT and PCBM, people start the work of 2002 onwards, and they get maximum of 6% efficiency, 7% efficiency will be there actually the organic solar cells. But still the cost factor is very, very high. So after 2010 people are publishing, but what they want, they say it's still efficiency is not good one. So that's why they almost stopped and they moved to perovskite solar cells, etc. But we can tune this molecule for different applications, we can get different moieties, that's our aim actually. Okay, so we choose Perlin. So Perlin is the conjugated molecule of, you can see it's a benzene ring like this actually. So in the Perlin, what happened? Perlin has good absorption component. It has epsilon for absorption will be very high, 80,000 moles minus 1 minus 1 actually, and it can absorb near to visible to IR region actually, and you see the colors of Perlin will be from like this colors. So this is the very important, colors are important for our system actually. Very important here, Perlin, where you have to functionalize. So we want to functionalize different positions actually. If you functionalize at your this position we call peri, for example 1, we gave 1 and 12 is called Bay positions. So compound is compound. If you put functional group R at 1 and 12 or 6 and 7, we call Bay Perlin. If you want to make 2, 5, 8 and 11, we call ortho Perlin. And if we tune 3, 4 and 9, 10, we call peri positions. So this peri and Bay positions, if you functionalize, based on the functionalist one, we get different properties, different colors can be noticed actually. You can see here, this is a one compound where we are tuning the group in peri position, that is we are tuning the group in peri position 3 and 4, we can put a imidazole moiety here actually, so peri position. So sometimes we can put your R group in the imidazole moiety, peri, and R group in the ortho, that is Bay position we might, so we can see compound peri and Bay. Here we can see peri and ortho we tune. So based on the tuning capacity, we can get different colors can be noted. That's the one important of the application of Perlin. So Perlin has very good applications because the compound has, we can functionalize at different positions based on the functional group, we can get different colors can be obtained. That's the advantage of your Perlin diamide. So we choose Perlin diamide. We don't want your PCBM, we don't want your P3HT, we tuned here actually. So you can see what happened here. If we tune the compound at the Bay position, we can change your electronic and optical properties. So we can change your optical properties. If you change your peri position actually, we can see that you can get a compound can be used for good color tuning, solubility and aggregation. So we can get a good solubility factor because organic compounds are generally soluble only solvents only. Sometimes they won't soluble. So we can get good solubility and color tuning etc. can be possible. So very important here we have to do theoretical predictions also. So how a compound should be in the HOMO positions and NO positions, we can see the compound will be delocalized. So the electrons are delocalized in different manner. Based on delocalization we get a good conjugation effect. Good conjugation leads to good colorful compound can be formed. That's the advantage of your Perlin compound. So we want to plan Perlin as one of the compound to make your solar cell, organic solar cells. So we choose different compounds. One is called electron donor, other one is called electron acceptor. So Perlin base will be called electron acceptor. Perlin base will be called electron acceptor molecules, whereas thiophene molecules, mostly thiophene molecules are electron donors. So we want to make a one compounds, mostly electron donors like this compound, this 3, and also we can prefer the electron acceptor, this 3. So So based on this 336 compounds, we want to make a solar cell in our application point of view. That's the important point we can notice. So first we go to this electron donor molecules. That's thiophene. Thiophene based electron donors. So we can prepare oligothiophene. That's called oligothiophene based compound. We want to prepare oligo based thiophene compound with good conjugation molecules can be formed for bulk heterojunction solar cell. So we synthesize the molecule. So we start with low molecule. See, in organic compound, we can start with hydroquinone plus XL bromide. So generally, these two compounds we prepare with the potassium carbonate, we get your compound. First step. Second step, this step will go with paraformaldehyde, we get second molecule. Okay, ortho position, we can put methyl chloride. Then we can do sodium cyanide, we can get your compound here, cyanide group. So this is a one series. Then we take a phthalic anhydride and then combines with aluminum chloride thiophene, we get a thiophene based compound, planar compound, and we can, this compound, thiolactane, and treatment with Grignard reagent method MGBR, we can get another series of compound, and then this is a Larson reagent, a very important organic compound we can use here. So Larson reagent can give you another combines to get a planar thiophene molecule. So this is a planar molecule. So we change your R1, either we can use H or C6H13 or C8, exile or octyl or hydrogen. So three compounds we can put. See, very important here, yield starts from 98%, we get yield of 58% only. Organic compounds very low yield. That's a drawback. To prepare this, it takes more than a year to go to this preparation. We need maximum 3 to 4 months. Sometimes yield is very low. We will repeat once again for everything actually to get a 1 year also for synthesis compound actually. Once we synthesize two compounds, we condense these two compounds to form monomer. We want to condense to form a monomer. So next step we want to form a monomer by no-angle condensation reaction. Adding these two reactions, we can get a condensation polymer, okay, monomer. This monomer, on treatment with the ferric chloride and catalyzed with hydrogen, we get a polymer can be formed. So we get a polymer of yield of 70%. So this polymer is what we want to use as a electron donor molecule for making the solar cell actually. So solar cell, first when the molecule form, be very important band gap calculation. So Dr. Jegadesan give our tutorial how to calculate the band gap. So we have formula optical band gap equal to 1240 by lambda onset. So lambda onset will be, we can take this value where the absorbance can be increased. So we can get around 620 or 625 is the absorbance onset, 624. So calculate this lambda onset, we calculate band gap will be 1.98. So we find the organic molecule which we prepared will be less than 2 band gap. So we want less than 2 means even 1.5 near to silicon 1.2. So we just move 1.98 here actually. So epsilon, I said organic molecule should be good epsilon. So we calculate epsilon also for the molecule. Epsilon is very high for this compound actually. Once we confirm this basic data, then we go to the fluorescence. The compound shows any fluorescence actually. So fluorescence also, there will be excitation wavelength and emission wavelength. When excitation wavelength and emission wavelength, you can see a doublet of peak. So mapping, these two will be matching. The two are matching is good for our tuning of organic compounds. So we choose the excitation wavelength and the emission wavelength matching with the compound. So it's a broad emission will be noticed, good for applications. Then we measure lifetime measurement. From lifetime measurement, we can say single deviation here. Single deviation which shows compound as purely organic molecule, no other impurity is there. So we get the calculated lifetime of the compound can be done. Very important polymer. Once the polymer formed, we got to see its thermal property. So Tg and dTA. So we can say weight loss method. So with weight loss is 235, first weight loss and second weight loss. So we can say stable, compound is stable up to 350 degrees Celsius can be stable, we can notice. So the organic compounds are stable and molecular weight we want to calculate by GC method, GPC method, that is called gel permeation chromatography method. So we get a molecular weight low. Generally polymer has high molecular weight, but we get your compound here because of big groups, we get a low molecular weight compound can be formed actually. That's our system we notice. So once we characterize the compound, we want to confirm the compound as a homolumen calculations. This also you did your, Dr. Jegadesan give homework for you, okay, tutorial. So how to calculate the homolumen calculation CV point of view. So take a electrode where you can cast your, by drop casting method, this is your galvanic electrode, this is your glassy carbon electrode on which we can coat your material by drop and then we can use the electrolyte, ferric chloride electrolyte, we can measure the cyclic voltammetry, it should be like this. So we from the cyclic voltammeter we can calculate the Ohm-Lumma value. We have formula for Ohm-Lumma will be here, E onset plus 4.72 electron volt. So from this value, substitute value, you can calculate your Ohm-Lumma positions. From the Ohm-Lumma we can calculate the band gap. You can see here 1.97 electron volt here, and your absorbance will be 1.98, almost same value we can use. Since this is organic molecule, we don't use your aqueous medium for doing cyclic voltammetry. We can do only organic medium, tetrabutyl ammonium phosphate as electrolyte, and we can do organic solar cell. So you don't use your aqueous AgAgC electrode, we use your non-aqueous AgAgC electrode as the counter electrode here, and then we can make. So that's the important point. For organic solar cells, we have to use all our non-aqueous, whereas because Dyson solar cell we can do aqueous medium. That's the advantage of organic and non-Dyson solar cell differences actually. Once you made this one, find the sample as good Ohm-Lumma, etc. actually, okay, we can make a solar cell. So we can calculate the band gap by DFT calculations and find the band positions, etc. And we can use here, first layer will be ITO, over which we can coat product PSS. Always you should be there, it's a binding compound, but coat one layer by spin coating, I can show cell. Then you can take your polymer, that's your polymer is electron donor. We use your electron donor polymer that we prepared, see in the compound oligotherapine, and then over which we can coat PCBM. Since we are only concentrating on here electron donor, electron acceptor may be same fixed one. We don't want to change it here, and then aluminum we can deposit. So once we deposit, we can make a solar cell. So this solar cell I can show you now. So this molecule we have Ohm-Lumma calculation we can do. How much the band positions are calculated, the 3 point, this one, etc. we can do by your density function theory method. So from density function theory method, we can see the compound as Ohm-Lumma calculations here. From which the band positions Ohm, first LUMO, that is the 1, and then Ohm minus 1, Ohm minus 2, Ohm minus 3, we can going. You can see the electron delocalization places where. In the case of your compound Ohm, all the compounds are in the conjugation benzene ring, okay, that's a thiophene point E. So in the case of alkyl group, no conjugation. Why we use alkyl group mostly for solubility product? Generally alkyl groups in long alkyl group we are adding here only for compounds to be good solubility in organic solvents. Similarly, if you go to LUMO side, you can see all the electrons on the thiophene moiety only. So this shows that thiophenes are good electron conjugation groups are providing here actually. From which we calculate the band positions and we can do. So once we take this one, we take the ITO, okay, we take the ITO plate. Once we take the ITO plate, so this is your organic solar cell, we make a 4 by 4. So we can see here, 4 by 4. So you can just pass it, the LED wires are changed actually, so I can just show you, transfer, you can circulate to others actually, okay. So this one, so what happens here, we take a ITO, first we can take a ITO, okay, then patterning, very important here, UV patterning. So this glass plate is ITO full, where we have patterned it. So this also ITO here, but we can remove by UV etching. So only this place will be your ITO, all the 4 places, pink one will be ITO. Remaining places are non-conducting. So this only 4 places are conducting, other places are non-conducting, we make non-conducting actually. Then we can put your compound spin coating of product PSS. We drop product PSS on the plate and then spin coating. So this may be here, like a red one, we can get your product PSS. So after which we coat your polymer, that is your oligotherapine based polymer, active layer plus PCU, both combined and then spin coating once again and it forms a surface. So 1, 2, 3, 4, 4 places we have to coat. We are coating on 4 places actually, so that's a 1. Once we go to the 4 places and then we can take your calcium we can use, or lithium fluoride, or aluminum we can use. Generally physics people say aluminum is better, low melting point, we can coat aluminum. So over which we can coat aluminum like this layer. So cross sectionally we can coat aluminum actually. So now this is your positive and this is your negative, both layer only we can conduct. Over which we can now put a encapsulant, we can put on another glass plate and cover it actually, okay, that's called encapsulant, we can get it. So then after encapsulated we can remove the moistures, because organic molecules, moisture is there, it won't work. So we have removed all the moistures from there by putting a vacuum medium. And this all will be do in a clean lab. Because for Dyson solar cell we don't need a clean lab, but this compounds when you make we need a clean lab. So we don't have such position here. We tried to do this one in IIT Kanpur. Professor SSK Iyer very much helped us actually. Also some work we did with Dr. Jegadesan, also one work we did actually. So this is the work we do, and we make a solar cell with the 4 concepts. You can see the 4 concepts. So we can take a sleeves, we can take a sleeves here. So this takes sleeves and connect actually. So that's the one I just showed you, circulated actually. So we did this one, and the cells are working for a longer period. So this is the method of fabrication of your organic solar cell. Very tough for student to, for us, when we start this work actually, very tough for us actually, because we don't have a green lab here in India, not India, you know, NIT. So we went to IIT Kanpur for doing this application actually. That's the application of your solar cell fabrication technology. So what happens, what is the mechanism? Mechanism takes place here. So mechanism here actually, we can see your anode is your ITO, a cathode is also ITO, over which we can coat your P3HT, PCM, and all the molecules, polymers are like this. So we can see it will be a, since it's bulk heterojunction, all the molecules, polymer, etc. will be like everywhere, and electrons are, exciton electrons are going here and there actually, that also possible. So what happened now, when I apply light energy, so we can notice the compound, actually. So the band positions are here. So we can see here, apply light energy, exciton formation. So organic molecule do not get exciton formation, and volts and electrons are formed. So volts will be valence band, electrons will be conduction band. So once the volts and electrons are there, this will be movement. We can say charge transfer. You can go like this actually. It's a exciton diffusion. So exciton diffusion takes place, and the molecule can move from donor to exciton level. Once it goes to exciton level, there will be charge transfer takes place. We can see exciton dissociation positions will be taken place, and charge transport moves. Once it charge transport moves, electrons and volts are separated now. We can see it goes back once again. So we can see that electrons and volts are separated. That will be good for the application of solar cells actually. So we can get the charge collection and volts collection on the other side, we get the light will be glowed. That's the mechanism of your organic solar cells we can notice. So this is the application of your organic solar cells you can notice here in this concept actually. So this is the yesterday Siddiq explained you how to calculate the fill factor, okay, and power conversion efficiency actually, okay. So you have dark current, when you do that without light energy, your IV current will be go like this. The black red one, it goes touch the line. No current, no voltage, voltage will be only 0, okay, and current will come something actually. When you apply light energy, the value will be changed to this one. You will get a J max, this is called J max, and this is called V max, and this is called P max. So we draw a curve V max and J max, we get your fill factor. We have formula here, J max is V max by JSC, that is VOC open circuit, J short circuit current multiply, we get your fill factor. Once you know the fill factor, we can calculate the efficiency, okay, that this is called P max by P incident. So incident lights we always use one sun, so one sun may be R mass 0, we can talk about AM0, AM1, AM1.5. Generally silicon solar cells give 44% efficiency only in the space, okay, where there will be AM0, R mass ratio will be 0, but if you reach the earth, it may be either AM1 or AM1.5 or AM2. Generally silicon, any solar cells they can put an angular form like this, 48 degree, we can say 48 degree above, let's go 48.2. So this will be good for your get good efficiency. So we also use the solar cells will be AM1.5 calculation to make a good efficiency can be 1. That's the application point of view. So AM1.5 is a good average for sun radiation, and for good standard calibration method can be used. So this factor will be used to calculate your solar cell efficiency can be done. Any solar cell, either organic or inorganic or physical, so anything we can do by this method actually. Once we did this one actually, okay, so we want to do. In the case of organic Dye-sensitized solar cell, we use current density versus voltage. But here, in the case of organic solar cell, we don't use current density. We use the logarithmic form. We use very important here. That's why we get a curve like this. We use a logarithmic form of current density. We don't use normal current density because the efficiency comes here very less actually. So to zoom the value more, we want to make a logarithmic form. So logarithmic form gives you a good value. So we make a logarithmic form. In dark, it may be almost 0. In the case of light, we get a value. So 0.6, 0.7 voltage. So we can see the voltage will be 0.7. And your efficiency will be around 6% to 7% actually. So that's one. Then we calculate your IPC, incident forward current come efficiency. Since organic molecule absorb almost visible light, we can see the visible light efficiency is more. That shows your solar cells are good application. So this molecule we look into the electrode fabricated in the AFM. So we can see the homogeneous, if I can notice, so homogeneously we can see the compounds are good blended actually, can be noted by AFM mechanical approach. So this is the first one, the first was the oligotherapy based system actually. So we get a good spectral range from 3 nanometer and we get efficiency of 1.3. This is we do in our laboratory, okay. So we do according to our sample, the 1.33%. That's very low accepted, but we make a organic molecule of your own choice. We don't purchase from PCBM or other molecule. We choose our own molecule. So that's why we get a low efficiency. Second molecule, so we want to tune more. The same oligopentane we want to make tune. What we do, instead of XL bromide, previously we use XL bromide, instead of XL we use octyl bromide because we feel that organic molecules are not soluble. We want to make more solubility improvement, so we use a long chain octyl, nonyl, etc. We increase the octyl compound, so we change your compound octyl portion. The same previously we use XL, now we use octyl actually, okay, same compound but octyl portions. Then we prepare your compound, this thiophene base, starting from different base, lactone base actually, and we get another compound. So all thiophene. And this we condense with your octyl base previous compound, and then we make a 3 compounds, C6H13 one compound, so we get a monomer, and then we take ferrichloride and make a polymer. So this polymer also once again electron donor, and we want to make movement, we want to make the movement towards visible. So you can this previously it being 644, now it becomes 750, the onset will be 750, the band 660, this is 660, the band gap will be 1.8, previously 1.95, 97 and 1.8, we tune the band gap. So epsilon also good, and lifetime also we calculated fluorescence also good actually, okay, and TGA and GPC results also noticed, we can find the compound as stability for longer period. So that's the one, we get only low molecular compound can be formed. So CV, HOMO calculations, this also support previously 1.8 to 1.78, almost nearly same band gap by electrochemical method as well as your system actually. So then we make a compound, we synthesize 2 compounds, so the band gap tuning by DFT calculations, we calculate the band gap positions of your compound. This is compound with octyl, and this is also compound V with octyl. We have different compound here, this position changes. Here C8, here C6. That's why we get 2 different compounds, A and B. And A and B we put one by one we make solar cell and we get a compound efficiency. So that's HOMO calculation to calculate the band gap and find the compound. It shows a very good value of, we can say 1.98 efficiency. We reached the 1.33 to 1.98 efficiency we can get. That's electron donor molecule like oligotherapine. Thiophene compounds are electron donor. This compounds show efficiency of 1.98. So see, 1.98 is low for us. That's why we try to improve, but we get only 1.8 efficiency in our laboratory. So that's the important point. Okay. So IPC we calculated. AFM we can see more compound will be more roughness of seen by compound organic molecule because solubility play a role actually. So we find the compound conclusion of this compound as tuned to sound 680 or 690 nanometer actually. Band gap is 1.87, so that may be good application. Once we confirm this electron donor is not good for a low efficiency, we want to make 2 electron acceptor. So we want to change the PCBM. Instead of PCBM, we want to make a Berlin molecule and we want to make a low cost. So we start with the compound nitroaniline and prepared a series. We can say treatment with carbon HCl, we form azo compound, and treatment furan, we take the other compound and cyclize here and formed this bifural compound. We get a bifural. We don't want sulfur group, we go oxygen group bifural compound. This one compound combines with perylene. So we take a perylene and we change your peri position, etc. First we change the peri position. So this compound, we change the peri position here reaction. So we get your compound peri position. So peri position change your color of the compound. So we get different colors. So we change the peri position and make a device. So this compound you can see the absorbance. It starts from 800, so good for our application. So we say band gap is low, we get 1.59. So very important, we want to tune the band gap, 1.59 electron can be obtained. That's the one we noticed here actually. So Once we tune the compound, emission lifetime we measured, so we get a good lifetime, good emission actually. So, and thermal properties, molecular weight of the compound 1800. So molecular weight is also increased here. Okay, the polymers formed this good one. We have used your compound as a stable compound. Once you confirm the compound is stable, we want to go to a Ohm calculation, cyclic photometry, and from cyclic photometry the band gap 1.34. That is 1.5, 1.34, almost same, because calculation some error will be there. So we have noticed the value will be nearly same values can be the Berlin. So we tune the band gap to low band gap value actually. Once we did this, we make a solar cell. Okay, we make a solar cell. So what we do, previously we used your PCBM. Now instead of PCBM, we put your donor Berlin base here. So if you use Berlin base, your donor may be P3HT. P3HT is donor actually here. We change known donor P3HT and then combine with Berlin based molecule and make a solar cell, make a device. We make a device. So we just change the one component. We don't want to change all the one. We change only here acceptor. Donor will be known P3HT. That's the important point we can notice here in this concept actually. So once we prepare this compound actually, okay, so we calculate the band gap by DFT calculations. So Omo. So you can see all compound electrons are only in the aromatic positions. You can see all compounds have electron relocation only in the aromatic compound. So this shows that the long chain compounds only for solubility part helpful. Conjugations are only mainly based on the your benzene ring. That is your benzene ring plays a conjugation effect actually. Okay. So we make a solar cell device, so which I circulated actually. So we find the compound has a very good efficiency. We get a current density is 2.83 and voltage is 0.92. Very important, the voltage, we increase the voltage to 0.92. So, but since the organic molecule fill factor we notice very low actually, okay, and efficiency also, due to fill factor is low, your efficiency is very low. So you can see this is the logarithmic form. We can see semi-logarithmic curve actually, semi-logarithmic curve of a compound which shows a value of 2.83 current density can be noticed. So this is a simple dark curve. Dark current goes here, light current goes here. But generally we don't want follow organic solar cell. People don't like this one. They like only this semi-logarithmic form. The semi-logarithmic form shows the compound as a current and voltage will be 2.83 millivolt and efficiency can be noticed. So this low efficiency etc. is based on your compound here. You can see here electron donor. Electron donor can be here. So from HOMO to donor P3HT takes place LUMO, and these electrons will go toward this path LUMO of your Berlin. The exchange of electrons can be possible here. So due to the exchange, we get a efficiency can be enhanced. That's the working of your donor series. We can see donor series can be helpful from this point of view actually. So when you do the IPC and your HOMO calculations, AFM is roughness factor play important role of compound. So since it is a bulk heterojunction, we have both the polymers are on a single layer, so we can notice the bulk heterojunction very good actually. So that's the one. We get a very important here 0.92 voltage. So we change the Berlin position. Now we want to change the Berlin at Bay position. When we want to change the Bay position, what happens? We want to see that's other concept. So we take an organic molecule, so Berlin. So we want to change your Bay position, so we take substitute your bromine here first, and then bromine we take another compound piperidine based here. So we put your compound Bay position. We don't change any peri position, we change the Bay positions. So that's the one compound we use piperidine. Second compound use a benzene with a terpyridine group, okay, benzene with a trimethyl benzene actually. So it's a functionalized compound, makes a planarity of the compound actually, so we put your Bay position. So we take these two compounds and then we want to see what happened. So earlier peri positions we get 1.93, here we want to make a Bay position and then tune. So that's why I told organic molecule synthesis is very tough, so how to functionalize everything we have play a role, and we have to do name reaction based on name reaction etc. and conditions etc. we have to get a good yield can be noticed. So once we get the compound, we make also this peri-Bay. So this is Bay change. Take this compound with the peri positions. Peri and Bay will be tuned. We tune peri and Bay positions actually. So in this molecule, Perry and Bay will be tuned actually. We get two different compounds, light blue solid and reddish brown solid. Color will be different. Light blue, you can see due to this compound, piperidine and your benzene with the trimethyl benzene, this compound, we get your colors will be changed. That's the important point can be noticed. So good absorber, you can see the absorbance, very good absorbance here, starts from your 800 nanometer, this 17, okay, that's advantage. So lifetime and fluorescence also, excitation emission will be noticed. We have a very good value can be find actually. So we find the lifetime as thermal properties. Thermal properties are stable for this compound, and we get a molecule by GPC method 1400 approximately actually. So we make a device. So Oumumu calculations. Oumumu calculation we can do for same two polymers. Band gap is 1.83, 1.77. So we can see CV are different molecules. Because of Perry and Bay portion, we get more oxidation potential than noticed. So we have calculated the band gap by Oumumu value calculations actually we can find. So we use your P3HT as electron donor, and we use our polymer as your electron acceptor. This will be one polymer 17 and another will be this one. So two different polymers we can do, and we do the solar cell fabrication method. So in this concept we can confirm the compound has actually Oumumu calculations. It's a very big molecule. So where the electron delocalization takes place. Electron delocalization is always on the benzene ring. You can see electron delocalization always on the benzene ring. So but when you go to LUMO position only it goes to your other moiety. For HOMO position mostly it is on the electron during benzene ring can be noticed. That's the important point of your calculation. The DFT calculation supports you where the electron delocalizations are in the molecule and how they will be playing an important concept of the system actually. So this energy level calculation we can do by band gap positions, okay, DFT, and then we can find the compound and make a solar cell device which is circulated same. So we find efficiency of the compound will be 1.23 and 1.18. Current will be very good, 2.16 milliamps. Voltage will be more. We can see voltage will be 1.124. That means 1000 millivolt, more than 1200 millivolt. Voltage we get increased. We increase the voltage 1200. Earlier we get 900, but we get a 1200 millivolt. So we increase the voltage much better, but we cannot improve the current actually. So we do, because since we are doing this, all the devices are outside our control. That means we have to go to take samples and go to IIT Kanpur and then do. So based on the slot, we are facing a lot of issues, and so we cannot do more than 3 cells or 4 cells over there. So that's why we cannot get much improvement. Since we do continuously, we can improve the efficiency further. So since we are not did enough work there, we have get which cell is good, best cell we find. So the cell I fabricated will be almost 8 years old. The way you are seeing now, it will be almost 8 years old cell we are doing. Now we are not working in this area because we are facing problems in doing fabrication. We stopped almost this work actually. So this is the IPC also we measured. So we compound a good IPC, etc., etc. So good for SOAS applications. So roughness factor is very important value. We can calculate roughness factor actually. You can see here. So roughness factor can be noticed 5.1. So roughness factor play important role in the compound actually polymers for making organic polymer solar cells. So AFM also supports our work why the cell has low efficiency based on roughness factor. So more roughness factor, the cell is not good actually. That can be also important point of this application. So we come to the short break or conclusion of this work actually. What we do, Perlin. So we choose a low cost. We do a low cost compounds in our laboratory. We don't use a PCBM. PCBM is very expensive. Instead of PCBM, we talk about Perlin as low cost comparatively. So we prepared a functionalized Perlin at Perry and Bay positions actually, and then make a solar cell, okay, which efficiency can be attained according to lab conditions is okay for us, but we have to improve more. So we are facing a lot of issues actually. Similarly, electron donor also oligotherapy based molecule we use, and we also get some efficiency. So that's our work we do. So electron donor and electron acceptor. So electron donor is a molecule, oligotherapy based one, and we can see the compound we have functionalized and etc., etc. We do many functionalized group, and we see the compound as planar compound, and the planar compound has to give a different application, the energy levels which will be which will be useful for calculations, etc. That's your electron donor molecule. Similarly, electron acceptor. So electron acceptor, Berlin we used and we do. So since the component has some stability issues, the R stability will be also there. So it plays some issues actually, but we get some we get some open up in our laboratory to do this one. So it's the initial period. When we do this one initial period, after that we stop this work actually in our laboratory. So I thank you for your understanding. Already most of the work, because since Dr. Jagdish gave an overview of this all organic solar cell, I just focused on one point, how we can fabricate solar cell. So what are the deficiencies? We can show the slides colorful organic molecule, but when you going to prepare the compounds and everything, we are facing the issues actually. That's why we show what is the issue we faced, how to improve. We have to improve. That's the important point. So you see, great sir he says solar photovoltaics is the future. So that's why people are mostly working in solar photovoltaics. Energy is the important point of view. So if you want to do work in energy, your future will be good actually. Okay, that's the important point I can say. So any important questions you have, I am happy to answer your questions. Okay. So thank you one and all for attending the lecture. Today is the last day, so we can share your feedback, everything for you actually. Thank you. Any questions? Yeah. 15. Lambda uncertainty is we have take this point where we cut it directly. This is liquid state actually. If you take solid state, you have to take the component this side actually. So generally you can take here the other way. Sorry? Yeah, we have to extrapolate only. This is absorbance graph, lambda max. You understand? If you take a transmitters mode, you are doing the one actually. In the case of your TAO to band gap, we are doing the other side actually. That band gap calculation. Extrapolate different manner actually. Since it's liquid state, where the onset, that means the line can be starts from 800, it comes here. The point where it increases, we call onset. The absorbance where it goes from 0 to increase actually, we call onset actually. That's the value we can use actually. In liquid state mode actually. But in the solid state we can take the other side. That means the graph will come like this, like this actually. So where we can cut the band gap, top plot we can make actually. But in the case of liquid mode, we can take onset starts from the place where it comes actually. So that's the important point we can notice. Okay. Yeah. Yeah. We are not doing electropolymerization, we do polymerization. Yeah. Preparation part. Hydrogen. So we want to see a compound here. The cyanide group is here actually, okay? Cyanide group here. And we want to condense with the group here, in this case, functionalized. We want to functionalize this place. Okay, this place actually, you can see here. We want to functionalize this compound in this place, in this group actually. So in this group we functionalize, so we make it active. To make it active, so we are a hydrogen reducing agent. Sorry? Hydrogen reducing agent. We don't reduce actually, we want to make your compound. In this case, CN group is there, no? The CN group is here, we can activate actually. We have to activate the compound here, CN group, and then only we can get a compound. Okay, we'll check the mechanism because this is the general mechanism we prepare based known mechanism. I will show you the mechanism. Yeah. We anchor the groups actually, we can see groups will be somewhat different. We can see this group. CN is there. CH2. This is called active origin, this one. This group only we are doing. Active origin only we are reduced actually. Okay. Anything? Yeah. Aluminium, and then we take a wires actually. Okay. Yeah. Solder directly. Yeah. Active area 0.25. There's 4 cell. This is 4 cell actually. One cell area, one cell area is 0.25. 4 cells are there actually. So we do this work series. Why we do? Because this is the work we do in the IIT Kanpur. There they said, if you do single cell, if there is any not working short circuits there, then it died. So we don't want to do such thing. That morphology has to do, that system has to do 4 cells, 0.25 cells in one cell. Even one cell is not working, you can use for 3 cells can work. We can test it actually. That's the reason they do 4 cells per time actually. So this one, my student has to go inside the clean room with all the bearings, everything actually. So he will stay here for 2 to 3 months to get this device actually, to get a good efficiency. He did 4 or 5 cells actually, from which we get some application actually. That's the important point actually. IIT Kanpur actually. Yeah. No, you can see the cell is not rectangle. The cell is only square one. This is a cell, no? You notice this one? Yeah. The cell area is only this one. This is the cell area 0.25. This is aluminum to take connections. This is your this is a full is ITO, for which they do UV etching. So they make only the ITO will be in this region. This ITO, this other regions we remove ITO. So this is only connecting. This is not connecting now. So that's make a UV. This taking this UV etching. It takes at least 3 days for this size glass plate to UV etching actually. So once you UV etch this one, this becomes non-connecting and connecting. On this connecting side, you go to a spin coating. You do layer by layer this material, coating only in this area, the 4 cells. Yeah, wipe it out. We clean. Okay. So once we clean this one, we do all the fabrication. Finally, we do put this glass plate and do aluminum deposition on this. So on the area of aluminum deposition only, we can take this leads actually. So that's why 4 cells will be this. This because our work to publish our work, we do some innovative. So that's the way 4 cell actually. This model is, so now all the things are known. Organic mold people are do. So how we have to separate different from others, we do this 4 cell and we say this is easy for making and then we get some efficiency. So that's the point we notice here actually. Okay. So only this area on this 0.25. This is only aluminum to take connections actually. Okay. So this is over which we have encapsulated we put actually to remove any oxygen. If you have oxygen in the organic solar cell, it won't work. So remove oxygen etc. and moisture and then put the cell encapsulate actually. Okay. So it's not just showing this the diagram is easy, but when you do this 3 months we tried actually with because Indian condition we don't wear gloves etc. We have to wear clean room dress also. So very tough for us to do this one actually when you start working actually. Okay, that's the point. So any other questions? Yeah. So thank you and all. Now we have tea break. After tea break, Dr. Jegadesan will take lecture for 2. That is 9 lecture and 10 lecture. And before lunch, he will complete all the things. And after lunch, we have only the valedictory period for just 20-30 minutes and then close the ceremony. Okay. Thank you.